Black holes do not act as cosmic vacuum cleaners, actively roaming the universe to suck up distant planets and stars. A black hole is an immense concentration of matter packed into a tiny volume. Gravity has crushed this mass until it reaches a density that defies standard physics. To achieve this density, you would have to compress the entire mass of the Earth, every mountain and ocean, into the volume of a single marble. As the most concentrated objects in existence, black holes change the physical rules of the space around them. Understanding these mechanics requires Albert Einstein's theory of general relativity. General relativity defines space and time as a single, flexible fabric. If you place a heavy star on this fabric, its mass creates a physical curve, like a weight on a trampoline. Gravity is the geometry of this curve. Smaller objects aren't pulled by an invisible force, they roll along the slope. Because gravity is a physical landscape, extreme density can create a curve so steep that it threatens to tear the fabric itself. A living star exists in a state of equilibrium. For millions of years, the outward pressure of nuclear fusion balances the inward crush of the star's own gravity. When the star exhausts its nuclear fuel, this outward pressure stops. Gravity immediately wins the war. In less than a second, the star's core collapses inward under its own weight. This collapse results in a singularity, a point where the entire mass of the star is crushed into an infinitely small, infinitely dense location. On the space-time grid, this singularity creates a literal bottomless pit. A black hole is born at the moment gravity permanently overcomes the fabric of spacetime, creating the region where the laws of physics as we know them no longer apply. To escape any gravitational curve, an object must travel at a specific speed called escape velocity. For example, climbing out of Earth's gravitational curve requires a speed of roughly 25,000 miles per hour. As the slope of a singularity becomes steeper, the required escape velocity rises. The universe has a speed limit, the speed of light, which is approximately 670 million miles per hour. The event horizon is the boundary where the required escape velocity exceeds the speed of light. Because nothing travels faster than light, any object or particle that crosses this line cannot climb back up the slope. Light cannot escape this geometric trap, which leaves the black hole effectively invisible to the rest of the universe. What happens to physical matter when it enters this extreme environment? Scientists use the term spaghettification to describe the stretching of objects as they approach the singularity. Because the curve is so steep, the pull on your feet is millions of times stronger than the pull on your head. This force stretches you vertically while squeezing you horizontally into a thin strand. The slope of spacetime becomes so severe that it overcomes the internal bonds of atoms, physically shredding the structure of matter. At the scale of a galaxy, black holes move from destroyers of matter to organizers of the cosmos. Supermassive black holes reside in the centers of most galaxies, weighing millions or billions of times more than our Sun. These giants act as particle accelerators, firing subatomic particles in blue jets that stream across space at nearly the speed of light. By regulating the movement of billions of stars and recycling gas through these jets, they provide the gravitational foundation for galaxies like our own Milky Way. A moment of wonder. These objects serve as the heavy hubs of the universe, providing the gravitational stability that holds galaxies together.